All right. So now I am recording. We are going to watch this video. This channel has some really good stuff. Like, if I don't know how much you guys are actually into calculus and math and like understanding. I have no idea. I know my senior year of high school, I was not. And I pretty much wasn't through college. And it really wasn't until I started teaching that I got like an appreciation for it. So I don't know where you guys are at, but this channel has some really good stuff and it's kind of cool to watch. So just to let you guys know that. 6183. I have to do a stop share, new share. I'm getting my transitions down, guys, just in time for us all to come back to school full time in August. I wish we would do that now. You know? But I don't think there's a chance of that. Okay, so you guys should be seeing Chrome. Turn the volume up. Minimize you guys at home so the people in here are not looking at your faces. As beautiful as they are. Here we go. All right.
When I first learned about Taylor series, I definitely didn't appreciate just how important they are. But time and time again, they come up in math and physics and many fields of engineering because they're one of the most powerful tools that math has to offer for approximating functions. I think one of the first times this clicked for me as a student was not in a calculus class, but a physics class. We were studying a certain problem that had to do with the potential energy of a pendulum. And for that, you need an expression for how high the weight of the pendulum is above its lowest point. And when you work that out, it comes out to be proportional to 1 minus the cosine of the angle between the pendulum and the vertical. Now, the specifics of the problem we were trying to solve are beyond the point here. But what I'll say is that this cosine function made the problem awkward and unwieldy, and it made it less clear how pendulums relate to other oscillating phenomena. But if you approximate cosine of theta as 1 minus theta squared over 2, of all things, everything just fell into place much more easily. Now, if you've never seen anything like this before, an approximation like that might seem completely out of left field. I mean, if you graph cosine of theta along with this function, 1 minus theta squared over 2, they do seem rather close to each other, at least for small angles near 0. But how would you even think to make this approximation? And how would you find that particular quadratic? The study of Taylor series is largely about taking non-polynomial functions and finding polynomials that approximate them near some input. And the motive here is that polynomials tend to be much easier to deal with than other functions. They're easier to compute, easier to take derivatives, easier to integrate, just all around more friendly. So let's take a look at that function, cosine of x, and really take a moment to think about how you might construct a quadratic approximation near x equals 0. That is, among all of the possible polynomials that look like c0 plus c1 times x plus c2 times x squared, for some choice of these constants, c0, c1, and c2, find the one that most resembles cosine of x near x equals 0, whose graph kind of spoons with the graph of cosine x at that point. Well, first of all, at the input 0, the value of cosine of x is 1. So if our approximation is going to be any good at all, it should also equal 1 at the input x equals 0. Plugging in 0 just results in whatever c0 is. So we can set that equal to 1. This leaves us free to choose constants c1 and c2 to make this approximation as good as we can, but nothing we do with them is going to change the fact that the polynomial equals 1 at x equals 0. Now, it would also be good if our approximation had the same tangent slope as cosine x at this point of interest. Otherwise, the approximation drifts away from the cosine graph much faster than it needs to. The derivative of cosine is negative sine, and at x equals 0, that equals 0, meaning the tangent line is perfectly flat. On the other hand, when you work out the derivative of our quadratic, you get c1 plus 2 times c2 times x. At x equals 0, this just equals whatever we choose for c1. So this constant c1 has complete control over the derivative of our approximation around x equals 0. Setting it equal to 0 ensures that our approximation also has a flat tangent line at this point. And this leaves us free to change C2. But the value and the slope of our polynomial at x equals 0 are locked in place to match that of cosine. The final thing to take advantage of is the fact that the cosine graph curves downward above x equals 0. It has a negative second derivative. Or in other words, even though the rate of change is 0 at that point, the rate of change itself is decreasing around that point. Specifically, since its derivative is negative sine of x, its second derivative is negative cosine of x. And at x equals 0, that equals negative 1. Now, in the same way that we wanted the derivative of our approximation to match that of the cosine, so that their values wouldn't drift apart needlessly quickly, making sure that their second derivatives match will ensure that they curve at the same rate, that the slope of our polynomial doesn't drift away from the slope of cosine x any more quickly than it needs to. Pulling up the same derivative we had before, and then taking its derivative, we see that the second derivative of this polynomial is exactly 2 times c2. So to make sure that this second derivative also equals negative 1 at x equals 0, 2 times c2 has to be negative 1, meaning c2 itself should be negative 1/2. And this gives us the approximation 1 plus 0x minus 1/2 x squared. And to get a feel for how good it is, if you estimate, say, cosine of 0.1 using this polynomial, you'd estimate it to be 0.995. And this is the true value of cosine of 0.1. It's a really good approximation. Take a moment to reflect on what just happened. You've had 3 degrees of freedom with this quadratic approximation. The constants C0, C1, and C2. C0 was responsible for making sure that the output of the approximation matches that of cosine x at x equals 0. C1 was in charge of making sure that the derivatives match at that point. And C2 was responsible for making sure that the second derivatives match up. This ensures that the way your approximation changes as you move away from x equals 0, and the way that the rate of change itself changes, is as similar as possible to the behavior of cosine x, given the amount of control that you have. You could give yourself more control by allowing more terms in your polynomial and matching higher order derivatives. For example, let's say you added on the term c3 times x cubed for some constant c3. Well, in that case, if you take the third derivative of a cubic polynomial, anything that's quadratic or smaller goes to 0. And as for that last term, after 3 iterations of the power rule, it looks like 1 times 2 times 3 times whatever c3 is. On the other hand, the third derivative of cosine x comes out to sine of x, which equals 0 at x equals 0. So to make sure that the third derivatives match, the constant c3 should be 0. Or in other words, not only is 1 minus 1/2 x squared the best possible quadratic approximation of cosine, it's also the best possible cubic approximation. You can actually make an improvement by adding on a 4th order term, c4 times x to the 4th. The 4th derivative of cosine is actually itself, which equals 1 at x equals 0. And what's the 4th derivative of our polynomial with this new term? Well, when you keep applying the power rule over and over, with those exponents all hopping down in front, you end up with 1 times 2 times 3 times 4 times c4, which is 24 times c4. So if we want this to match the 4th derivative of cosine x, which is 1, c4 has to be 1 over 24. And indeed, the polynomial 1 minus 1/2 x squared plus 1/24 times x to the 4th, which looks like this, is a very close approximation for cosine x around x equals 0. In any physics problem involving the cosine of a small angle, for example, predictions would be almost unnoticeably different if you substituted this polynomial for cosine of x. Now, take a step back and notice a few things happening with this process. First of all, factorial terms come up very naturally in this process. When you take n successive derivatives of the function x to the n, letting the power rule just keep cascading on down, what you'll be left with is 1 times 2 times 3, on and on and on, up to whatever n is. So you don't simply set the coefficients of the polynomial equal to whatever derivative you want. You have to divide by the appropriate factorial to cancel out this effect. For example, that x to the fourth coefficient was the fourth derivative of cosine, 1, but divided by 4 factorial, 24. The second thing to notice is that adding on new terms, like this c4 times x to the fourth, doesn't mess up what the old terms should be. And that's really important. For example, the second derivative of this polynomial at x equals 0 is still equal to 2 times the second coefficient, even after you introduce higher order terms. And it's because we're plugging in x equals 0. So the second derivative of any higher order term, which all include an x, will just wash away. And the same goes for any other derivative, which is why each derivative of a polynomial at x equals 0 is controlled by one and only one of the coefficients. If instead you were approximating near an input other than 0, like maybe x equals pi, in order to get the same effect, you would have to write your polynomial in terms of powers of x minus pi, or whatever input you're looking at. This makes it look noticeably more complicated, but all we're doing is just making sure that the point pi looks and behaves like 0. So that plugging in x equals pi is going to result in a lot of nice cancellation, leaves only one constant. And finally, on a more philosophical level, notice how what we're doing here is basically taking information about higher order derivatives of a function at a single point, and then translating that into information about the value of the function near that point. You can take as many derivatives of cosine as you want. It follows this nice cyclic pattern: cosine of x, negative sine of x, negative cosine, sine, and then repeat. And the value of each one of these is easy to compute at x equals 0. It gives this cyclic pattern 1, 0, negative 1, 0, and then repeat. And knowing the values of all of those higher order derivatives is a lot of information about cosine of x, even though it only involves plugging in a single number, x equals 0. So what we're doing is leveraging that information to get an approximation around this input. And you do it by creating a polynomial whose higher order derivatives are designed to match up with those of cosine, following the same 1, 0, negative 1, 0 cyclic pattern. And to do that, you just make each coefficient of the polynomial follow that same pattern, but you have to divide each one by the appropriate factorial. Like I mentioned before, this is what cancels out the cascading effect of many power rule applications. The polynomials you get by stopping this process at any point are called Taylor polynomials for cosine of x. More generally, and hence more abstractly, if we were dealing with some other function other than cosine, you would compute its derivative, its second derivative, and so on, getting as many terms as you'd like, and you would evaluate each one of them at x equals 0. Then, for the polynomial approximation, the coefficient of each x to the n term should be the value of the nth derivative of the function, evaluated at 0, but divided by n factorial. And this whole rather abstract formula is something that you'll likely see in any text or any course that touches on Taylor polynomials. And when you see it, I want you to think to yourself that that constant term ensures that the value of the polynomial matches with the value of f. The next term ensures that the slope of the polynomial matches the slope of the function at x equals 0. The next term ensures that the rate at which the slope changes is the same at that point, and so on, depending on how many terms you want. And the more terms you choose, the closer the approximation, but the trade-off is that the polynomial you get would be more complicated. And to make things even more general, if you wanted to approximate near some input other than 0, which we'll call a, you would write this polynomial in terms of powers of x minus a, and you would evaluate all the derivatives of f at that input, a. This is what Taylor polynomials look like in their fullest generality. Changing the value of a changes where this approximation is hugging the original function, where its higher order derivatives will be equal to those of the original function. One of the simplest meaningful examples of this is the function e to the x around the input x equals 0. Computing the derivatives is super nice as it gets, because the derivative of e to the x is itself. So the second derivative is also e to the x, as is its third, and so on. So at the point x equals 0, all of these are equal to 1. And what that means is our polynomial approximation should look like 1 plus 1 times x plus 1 over 2 times x squared plus 1 over 3 factorial times x cubed, and so on, depending on how many terms you want. These are the Taylor polynomials for e to the x. Okay, so with that as a foundation, in the spirit of showing you just how connected all the topics of calculus are, let me turn to something kind of fun. A completely different way to understand this second order term of the Taylor polynomials, but geometrical. It's related to the fundamental theorem of calculus, which I talked about in chapters 1 and chapters 8, if you need a quick refresher.
All right, we'll stop there. Isn't that good animation? How do they do that? This is good stuff. Get the functions like hugging and curves and stuff. I don't know. Beyond me. All right. So let me stop that share. Share screen. Share Elmo. Share. Stop AirPlay. Switch source. No. There it is. Open up the notes for today on Taylor and Maclaurin polynomials. So it's pretty much impossible to predict what type of FRQs you're going to come across on your AP test. But with almost 100% certainty, I think the last, I don't even know how far back you can look. Question 6 on the BC exam is a Taylor polynomial Taylor series FRQ. And so today is just going to be kind of like the foundation, like how do we develop these things? As we kind of go through this chapter, you're going to get a lot of FRQ practice on these things, because you'll be able to see the types of questions that they ask. So
the Elmo is displaying weird.
You're displaying weird. I don't know if I actually shared the Elmo. Is that it? Is that good or no?
That's good.
That's better? All right. Thank you for being bold to shout out during the Zoom when others may not be so bold. So bottom line, what these polynomials do for you, these Taylor / Maclaurin polynomials, now I'm going to talk about why it's Taylor / Maclaurin polynomials. For most of that video, it was like centered when x was 0. We say centered when we're talking about like what input do we want to be really close to. Anytime you're centered at 0, we call that a Maclaurin polynomial. Anytime you shift it and you want to talk about, well, let's get to values really close to x equals 2. I want to approximate, 2.1 or 1.9. So we're talking about being close to 2. That's called a Taylor polynomial. So anytime you're like shifted. So Maclaurin is just a really, what's the word? Maclaurin polynomial is basically a Taylor polynomial, just at 0. In fact, there's not even a point to even call it a Maclaurin polynomial. You can just call it a Taylor polynomial centered at x equals 0. It's kind of like when we did mean value theorem and Rolle's theorem. You guys remember that? That was a long time ago. But Rolle's theorem only applied to when the average rate of change was 0. The mean value theorem applied at any rate of change. So the mean value theorem like encompassed Rolle's theorem, kind of like this. So the bottom line of what it does, I'm pretty sure from what my research, that what your calculator does, when you guys enter like sine of 5 in your calculator doesn't know what sine of 5 is. Your calculator knows the Maclaurin polynomial to some power. I don't know where it stops, but it knows the polynomial that represents sine and puts 5 in for all those x's and does an approximation. That's how these calculators get programmed, as far as my understanding goes. It takes the corresponding Taylor Maclaurin polynomial and uses it to approximate. That's why sometimes when you get values, like once you get way off to the end, like some of your calculators will have different answers once you get out to like the 1 billionth decimal place. Like some of you guys get little variations. That's kind of why. But we're going to talk about how we kind of develop these things. You are going to have to know this formula. This is a formula that you guys 100% have to know, but it's kind of nice in that I'm going to show you guys some little tricks to help you. It always starts with the initial constant. But then what I want you to notice is in terms of the derivatives and the powers and the factorials, they always match. Like when you get to, if you look out here to the second derivative, notice we need the second derivative of our function. That corresponds with x squared, and it's divided by 2 factorial. Like all the 2's go together. Second derivative, it's x squared, it's over 2 factorial. It's the third derivative, it's x cubed, it's over 3 factorial. They all match up, which makes these things pretty nice to work with and pretty easy to kind of remember. So we are going to start with finding the nth Maclaurin polynomial for f of x equals e to the x. A lot of times on FRQs, what they'll say write the first 3 non-zero terms. Like they'll specify like how many terms they actually want you to write of these polynomials. They'll tell you that. And the reason they say non-zero is because on that cosine example he gave, like, what was it? The second term was 0, the fourth term was 0. Is that what it was? Like every other term zeroed out. So that's why they'll say non-zero terms. We'll take a look at that. So what we need to do is this. The first thing I want to write is that formula. Okay. Anytime you learn kind of a new formula, I would write it out. But the nth Maclaurin polynomial, we're going to notate it as p sub whatever. If we were looking for the third degree polynomial, we would write p sub 3. So the nth degree Maclaurin polynomial in general is going to be f of 0. Notice it says Maclaurin, so I know my x value is 0. My input is 0. That's how I know that. Okay, we got to hone in on that word Maclaurin. We're at 0. So it's f of 0 plus, now you don't have to write this for this, but I am for kind of understanding purposes. It would be whatever f prime of 0 times x to the first power over 1 factorial would be. Now all that can simplify. You don't have to write x to the first. You don't have to put over 1 factorial, but just to kind of drive that pattern home. Plus, it would be whatever f double prime of 0 is. And we're going to find those values. Like that's going to be our procedure. We're going to find those derivative values times x squared over 2 factorial. Plus, and we'll do the third one, and then we'll do the nth one. F triple prime of 0, x cubed over 3 factorial, plus dot, 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 plus all the way until we get to the nth term. So it's going to be the nth derivative, which we notate as f, and then we put that little n up there, times x to the n over n factorial. Really all we have to do to answer this question is figure out what these function values are. Like that's what we need to find. Everything else stays put. We just got to find those values. We got to find f of 0, f prime of 0, f double prime of 0, and so on. So off to the side, here's how I'm going to do that. We're dealing with e to the x, right? So f of x equals e to the x. The way I like to do these is completely up to you, but I'm going to go ahead and just kind of write out a bunch of derivatives. This one's easy because they're all just e to the x, but like f prime is e to the x, f double prime, e to the x, f triple prime, dot, dot, dot. The nth derivative is e to the x. So I'm just going to list out a bunch of derivatives of that function that's given. E to the x is the most simplistic one. But then I want to find all those derivative values at 0. Right? That's what I'm trying to find. I want to find f of 0 and then f prime of 0 and f double prime of 0. I want to find all those values to plug into the formula. So f of 0 is just 1. And in fact, for this, all of them are just 1. F prime of 0 is 1. All those derivative values are 1. So for our answer, all we do is take all those things I circled and just replace them with 1. And what we're coming up with is the Maclaurin polynomial for e to the x, the polynomial that will approximate e to the x. So p sub n of x, the nth Maclaurin polynomial for e to the x would be 1 plus 1 times x over 1 factorial, so just x, plus 1 x squared over 2 plus 1 over 6 x cubed plus dot 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 plus 1 x to the n over n factorial. So there's going to be 4 that you guys have to memorize. I guess you don't have to, but they're really going to make your life easier on multiple choice questions and FRQs if you just have them memorized. So I'm going to give you guys a sheet. You guys at home won't get this sheet until next time. You're going to have to remind me. I thought about putting it on Canvas. Maybe I did. Maybe I surprised myself. I don't know. But this is kind of like we had that series convergence sheet. These are the 4 that you guys have to kind of know stone cold. You actually, so the more I started to think about it, you really only need to know sine of x. Why? Why would sine of x tell you what cosine of x is? Yeah, like if you just know sine, I've never really taught it this way. I would know them anyway, but if all you know is sine of x, so here's the sheet, guys, for you guys at home. In fact, you just take a picture of it, I guess, but I will pass it out to you. If all you know is the sine of x polynomial and you differentiate both sides, you'll get to the cosine. Like if you take the derivative of all these terms, you'll get back to the cosine. So you really just need to memorize sine, I guess, and e. The bottom one is really nice because the bottom one is just like the geometric series formula. Like look at the right side. Notice how the first term is 1 and we're just multiplying by x every time, like it's a geometric series. And so this is really your geometric formula right here, where 1 is your first term and then it's 1 minus r on bottom. R is what you're multiplying by. So this is really just your geometric series where the first term is 1 and you're multiplying by x every single time. So that one's pretty easy to kind of keep straight to. All right, back to the notes. So this one says we're dealing with natural log of x. Find the Taylor polynomials. Notice they say Taylor now because we're going to center at c equals 1. It doesn't make anything like that much harder. All it does though, in that formula where we had x to the first and x to the second, now we have to have x minus 1 to the first, x minus 1 to the second, x minus 1 to the third. So we're basically shifting everything to the right 1 unit. So it makes things not as fun. All right, first thing I'm going to do is write f of x and a bunch of its derivatives off to the side. So f of x is natural log of x. F prime is 1 over x. We got to find the derivative of this, which if you think about this as x to the negative first, it's negative x to the negative second. So negative 1 over x squared. And that's just negative x to the negative second. So that's going to become positive 2x to the negative third. So 2 over x cubed. And it wants us to go, notice it says the 0th, the first, the second, the third, and the fourth. So we're going to go to the fourth derivative. Now I'm going to evaluate all of these functions at 1. Last time I put in 0, but now we're going to plug in 1 for all of these. So f of 1, natural log of 1 is 0. F prime of 1 is just 1. Negative 1. I don't know why I like these so much. I do. They soothe me. I don't know why. Anybody else soothed by them? Really? Telepathically?
Yeah.
All right, so I'm going to list these out in order. It wants us to find, I mean, what would you call that? The zeroth? Huh? You not? I don't know. But that's just the first constant, which we found here is 0. I guess we should write what this formula is end up gonna looking like. That's probably better to start out with. So for this particular problem, the nth Taylor polynomial of natural log of x centered at c equals 1 is going to be whatever f of 1 is in this case. Like notice up here it was f of 0, f prime of 0, f double prime of 0. Well, now we're at 1. So all those zeros become 1s plus f prime of 1. Here's where you need to be careful. It's not times x to the first. It's times x minus 1 to the first. You can put over 1 factorial. Plus f double prime of 1 over 2 factorial times x minus 1 squared. You're just following that pattern. On the notes, I listed out like I found all of them. I don't know why I did that. 0, the first, the second, the third, the fourth. Let's just write the fourth. You guys okay with that? We're just rewriting all of them until we get to the end anyway. So we'll just do the fourth. So we're really just following this formula that we just wrote up here, plugging in all these f values that we found. So the first one is 0, which I guess you could put or not. But this is where if it said like the first, say it said the first 4 non-zero terms, like that one would not count. We would have to put 4 others. So you just need to be careful when it uses that word non-zero. Plus, well, the next one is 1 over 1 times x minus 1. So that would be the next term. The next one is the second derivative. So negative 1, oh shoot, minus 1 over 2. The next one's positive 2. So plus 2 over 3 factorial. I'm out of room. Minus 6 over 4 factorial. I got it. Got it in there. So what I pulled up and almost not blocked. Plain and stupid. So you know you're getting old. Oh, it is. I just wrote 2. 2 factorial is 2. It is. I probably should. There you go. I mean, if this was the question you were asked, I guess technically you should write every single one. They're not going to ask it that way though. Yeah. What do you guys think of these? Did you guys understand the physics stuff at the beginning that he was talking about? Small angle approximation stuff?
Like trying to find the period of a angle.
Yeah.
It only works with really small angles.
Yeah.
So I made that connection.
So you have talked a little bit about that. All right. Next. We're not going to do all of these, by the way. So find the Maclaurin polynomials 0, 2, 4, and 6 for cosine of x. We'll just find the sixth one. We'll just focus on that. But if you have that sheet memorized, like if you already know what those terms are, you don't have to go through what we are about to go through. A lot of times on an AP test, again, you guys will get a lot of practice with these FRQs. We're going to do a lot of them, but it'll say, like, a lot of times you get a point or two, it'll say write the first 3 non-zero terms for the Maclaurin polynomial for cosine. And if you just have these 3 things memorized, like you legit just write those 3 terms, you get a point for knowing it. If you don't have it memorized, then you have to know how to generate it. It just takes time. So, all right. It says use the 6th degree polynomial and to evaluate or approximate cosine of 0.1. All right. So first thing, we're going to list out cosine and up to its 6th derivative. That's not bad. It's kind of fun. Are we having fun? Are we having fun?
Yes.
Okay. In algebra 2, I got to teach them about asymptotes and holes today. It's one of my favorite lessons.
It's pretty fun.
It is good. Like, it's new. It's like different. It's, yeah, I enjoyed it. Mm-hmm. I like teaching logs and I like teaching rational functions. Those are my favorite things. And now here you are. So it says Maclaurin, which means we're centered at 0. 0 is our input, which is really nice. You don't have to put x minus whatever, just x. So we're going to find f of 0. I'm just going to shut up. You guys don't need to hear me talk to do all this stuff. Do you guys see that? You guys are talking about the guy that looks like he's dead. So he's in the hospital. He's in the hospital. I saw it on the news the other day. I was like, oh my gosh, I would not have even known who that guy was if you guys weren't talking about him in class.
And he looks dead. He looks very old. I thought he died like in my mom's high school. I thought he was
The little thing would be doing crazy stuff all the time.
So what I find interesting, because eventually we're going to get into Taylor's series, which is basically an infinite series that models these functions instead of a polynomial. And what I've learned is you need to be very careful when you put your like plus dot, 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 and when you don't. When they ask you to do a polynomial, like you have to end it. You don't put like plus dot, dot, dot to like infer that it's still going on. But when you guys do a series, you do need to make sure you put plus ... to imply that it is going on forever. So those actually can award you points or cost you points, like when you put the ... and when you don't. So this is the 6th degree polynomial for cosine of x. It does say use it to approximate the value of cosine of 0.1. I'm just going to write these numbers out, but basically what they're saying is this polynomial should basically tell you what cosine of 0.1 is. It should give you a very, very close approximation. That's the whole point of what we're doing. And so I'm going to show you guys what you get if you do plug 0.1 in for these x's, and I'm going to tell you what cosine of 0.1 actually is. We'll see how close they actually are. So this polynomial evaluated at 0.1 is 0.995004165,278. That's what this polynomial is if I plug 0.1 into all those x's. Well, prepare to be amazed, because cosine of 0.1, I was talking and then I about put 0 and I didn't, is 0.990041665. I don't know why I stopped there, but that's where like they start to differ. Look at that. Isn't that crazy? We have cosine, some trig, transcendental function. And here we just have some simplistic 4-term polynomial. Look how similar those are. Holy smokes. Thank you, Maclaurin and Taylor. We'll have to look up their pictures here in a second. I don't know which came first. We're not going to do the final two. You'll get more practice. But I do want to kind of talk about what will happen is they'll say, and again, we're going to get practice with this, but just to give you an idea, a glimpse ahead of time, they'll say stuff like, find the 6th polynomial for x cosine x. You're going to be doing some manipulations with these things. Like if you know cosine, which we do, like we know this is cosine, and we want to find an approximation for x times cosine of x, we're basically just multiplying every term over here by x. This is how they're going to like transform using these things that you have memorized. Or they'll say something like, find the approximation for cosine of 2x. Well, if you know cosine of x, then where all these x's are, you replace all these x's with 2x instead. We're using the cosine of x and then using these transformations. So this is where having those things memorized are going to be really nice. That way you don't have to like write, the 6th derivative using chain rule 6 times and evaluating and stuff. You just have it memorized. But we'll get a lot of practice. All right. You do have an assignment, pretty short. There's only like 5 or 6 questions that's on Canvas. So you guys at home, you are free to go. Stay classy. Peace out. Stay out of trouble this weekend.
Have a good weekend.
You too. All right, let's take a look at, I wonder what the guy's first name is. Probably would help. I wonder if there's pictures of these guys in the book. I don't have to Google it. We're going to find out. We'll be able to look at their pictures and know who's better. Ooh, this guy looks fierce. William Rowan Hamilton. I would not want to fight that guy.
Inspectors, get him out of here. That's it.
That guy. Whew. Man. You find him? Colin Maclaurin. I like that name. Brooke Taylor. I think this guy would be pretty easy to take down.
Yeah.
He looks feeble. It's got to have, I don't know what chapter these are in. 9. Here we go. Colin Maclaurin. He died when he was 48 years old. There's Taylor. Maybe there was a picture of Taylor earlier. You found him? Oh, he looks, he's got a scowl. He doesn't look happy. What's this guy?
Yeah.
Is that the same guy?
Yeah. No, I thought the first guy was, this
It's gotta be the same guy. I wonder who came first. Let's see, were they around the same time frame? I forget when the other guy died. Wow. Yeah, but what year? So Taylor died in 1731. Maclaurin died in 1746. So he lived 15 years later. Taylor, yeah, Taylor was born, he was older. Well, he was born first, I should say. I want to know the history. I want to know, like, did Taylor come up with this stuff and Maclaurin like stole his thunder with 0? Or did Maclaurin do it with 0 and then Taylor like expanded it?
I think it has to be that way, otherwise we just call them.
I would think. Google it. You're on Google, right?
I don't know.
We'll accept it as fact. Don't tell your English teachers I said that. Oh, that can't be good. They're both English.
And Philip actually comes in and he's like, that don't look good. So he's like, yeah. In 1713.
My mom was watching.
What about Maclaurin? So you think he came through and just stole his thunder and said, at x equals 0, it's now named after me? Well, that's possible. A lot of those guys were doing stuff like in their late teens. So Taylor came first.
Oh, it says nevertheless, received credit for his usage. So,
I wonder why. I wonder why they like gave him such clout, Maclaurin. Like if Taylor was already a thing, why not just use Taylor as 0? Why even give it a name?
yeah,
It seemed like he like greased some palms.
yeah,
Like
they attribute this series to the Taylor series.
huh.
Blue back.
Yes. See, math history is fun. When you learn it on your own terms, not when like
Oh, yeah, no, I
you're
don't.
forced to learn things. Yeah. But when you're free to Google whatever you're curious to know.
Oh, no, if I went to a TED talk, I'd be like, that's sick. And I need to go to graduate. Like those TED videos, I love them. I watch those.
Ted what?
TED Ed, like, this is short one. Like the animated one usually. I love those. There's one, there's one about Swan Lake. It's like one of the hardest things about it. Like, she does like a bunch of things in a row. I like watch that all the time.
I just realized I didn't stop recording.